All right, everybody, welcome to Math with Grace. Hello, today we will be doing Geometry, Book 1003, Sections 2 and 3, which is basically pages 37 through 58. Page 37, or Section 3, gets us started all about parallel lines. Okay, and parallel lines are lines that are in the same plane and have no points in common. Basically, two lines run parallel when they run directly next to each other at any distance on the same plane, but they're not tilted. They will never ever touch. Okay, parallel lines run side by side forever and ever, amen. Okay, because we know that lines go on forever and ever. They can be far, they can be close, but they never are tilted enough that eventually they would touch each other. Okay, they are always equidistant from each other. They are exactly the same distance from each other now as they will be in 1,000 years. Okay, that's what makes lines parallel. So looking on page 37, we see that a figure drawn here. And if your brain and your eyes are like mine, sometimes I have a problem figuring out which part of the picture is in the foreground and which is in the background. The dotted lines here emphasize edges that are in the background. Edges that if we had this shape as a solid block, that we couldn't see. But sometimes, and maybe you're like this too, sometimes my eyes play tricks on me and it actually puts those dotted lines in the foreground. And so my brain sees it as a dimensional shape that's in the front. But I have to remember that the dotted lines are in the background. Okay, and so then they say here that segment AB, which is right here, and segment AD, okay, which is here, intersect at point A. AB and DC are in the same plane, and that plane is the top plane of this box, okay, this rectangle. But they do not intersect, okay? They do not intersect because they are parallel lines, all right? AB and EF, which is down here, they are in different planes, okay? AB and EF are not in the same plane. They cannot be in the same plane. It just doesn't work out that way. And therefore, but they still do not intersect, but that does not make them parallel. Because AB and EF are in different planes, they cannot be parallel to each other. Because if they were in the same plane, then they would intersect, right? But they're not in the same plane, and therefore they are not parallel. Something that might help you, and this is the only box I could find, I'm not trying to be pompous or anything, but is having a actual three-dimensional shape to look at. If drawings of three-dimensional shapes, and trust me, when I start drawing them, they're going to probably look terrible. If the drawings are confusing to you, then just get out there in your house somewhere and find a three-dimensional shape that you can use. I have a rectangular solid here, and so I can look that AB and DC are indeed on the same plane, which is the top of my box, and they are indeed parallel to each other. So do not be ashamed or think that it's silly to get something to help you, some type of box or shape that you can hold on to and actually physically look at, because trust me, it can be very useful, especially when your eyes are kind of throwing this shape into weird dimensions. Okay, so parallel lines are two lines that are equidistant from each other at every single point, therefore, and they're on the same plane. They're called parallel lines. They will never cross, and they're on the same plane. Those are parallel lines. If we turn to the next page, which is page 38, we see a definition for skew lines. Now, a skew line are two lines that do not lie in the same plane. So remember on the page before when they were talking about AB and EF, that they were lines on a different plane? Those lines are considered to be skew. Okay, they are on a different plane from each other. A line and a plane are parallel if they have no points in common. Okay, here they have line L and plane A, and they're considered parallel because they have no points in common. And if you're looking at it like, what the heck? Think of this piece of paper and this line traveling over the piece of paper, okay? See the difference? I'll try to get it here in there. See it like that? Okay? That's what they're talking about here in these models. All right? They're parallel, but they're not in the same plane. Well, skew lines can be parallel, but they do not lie in the same plane. Okay, so really they're not parallel, because what's the definition of parallel lines? That they have to be in the same plane. So while AB and EF would never touch because they are not in the same plane, they're also not parallel. Okay, so askew lines are two lines that do not lie in the same plane. AB and DF are two lines that do not lie in the same plane. All right, they are skew lines. Continuing over here on page 39, they're talking about parallel planes, planes that have no point in common. Again, think of two pieces of paper running alongside each other. Okay. Or think of two walls of your house, two opposite walls of your house, okay? They are parallel, right? Your front wall and your back wall of your house, but they are not in the same plane, right? They are singular planes. If we go back to our solid box, okay, and we look at this plane of this side of the box and this plane of this side of the box, okay, they're parallel. They will run on and on forever without ever touching, right? They are called parallel planes. They run parallel to each other and have no point in common. If this side of the box was tilted like this, eventually those two planes would come in contact with each other way over there, right? So they wouldn't be considered parallel because they would have points in common. Once they intersect, they have a point in common. That they're no longer parallel. So remember, parallel planes, okay, don't have any points in common. And here are some examples of parallel planes. And at the bottom of the page here, they give the example of your house. Your floor and your ceiling are parallel planes. This wall and this wall are parallel planes. The door wall and this chair wall are parallel planes. Okay, those are examples of parallel planes. On page 40, we get our next theorem, and that's theorem 310. 310 tells us if two parallel planes, here we have two parallel planes, A and B, are cut by a third plane, the lines of intersection are parallel. So they're basically saying if plane A and B are parallel and plane C comes along and cuts them in half, well, not in half, just cuts across them. Okay, I don't want to say in half because that's not true. This line here, line L, and line M are parallel. All right, that's what the theorem is telling us. Now, this transversal plane, plane C, could have cut across on an angle and not straight. They make it look pretty straight. It could have cut across at an angle. Either way, those lines it creates would still be parallel. And here's why. All right, we're going to read through it. So there we are given that plane A and plane B are parallel. That's what this means. Remember, parallel, when we mark it down, we just mark two lines. Plane A and B are cut by plane C, creating line L and line M. All right, and they want us to prove that L and M are parallel. So let's start out. Here, they don't... This is what I don't like about their examples is they want you to set them up when you do your work a certain way, but they're not always set up that way in your examples. Okay, but let's just look at what they say. Line L and line M are in the same plane. Okay, they are, right? L and M are in the same plane because they were created when plane C cut across. Okay, given in plane C, right? Right here. Line L lies in plane A, and line M lies in plane B. Okay, so line L is just as much a part of plane A as it is part of plane C. Just like line M is just as much a part of plane B as it is plane C. That's what they're saying. And their reason is the intersection of two planes is a line. We learned that a couple weeks ago, right? When two planes intersect, one line is created. Plane A, plane B have no point in common. A and B have no point in common. That is very true because it's the definition of parallel planes, and we've already been shown that A and B are parallel. So we can say that. Line L and line M have no points in common. Okay? L and M are part of planes A and B respectively. And when a line is in a plane, it is part of that plane, right? We learned that as well. So then they go to this L is parallel to M because that's the definition of parallel lines in the same plane, plane C, and having no points in common. Now, like I said before, I'm reading through this. These proofs are much harder and more complicated than the proofs that we are working on. But I just want to show you how they got from point A to point B. Now, I want to look at the problems on page 41. And your directions are, for each statement, write always, sometimes, or never true. Now, these problems are kind of complicated sometimes. They really are trying to get you to think hard about what they're saying, because a little bit of untruth can make something untrue. All right, so they're trying to make sure you're weeding out and you're making your statements when we do proofs flawless, absolutely truthful, 100%. So let's first look at the first one. Skew lines are parallel. So is that true? Are skew lines parallel? Remember what we just talked about, skew lines, right? They're lines that are not in the same plane. And if they're not in the same plane, can they be parallel? Because being in the same plane is the definition, it's part of the definition of being parallel, right? So these are never parallel. Skew lines are never parallel. All right? Number 2, a line on the wall and a line on the floor are skew. So think of your room right now that you're sitting in. If there's a line on the wall and a line on the floor, are they skew? Which basically means, are they in different planes? They are, right? Sometimes they are skew. Sometimes, though, they will also intersect. Okay, your line on your, and I'm doing it flat so you can see it, but the line on your floor will sometimes intersect the line on your wall, and then they do fall into the same plane, okay? Because that, you can see from my cross section, is the same plane. But if your line on your wall and your line on your floor look more like this, here, I'll use a pen, okay? Then yes, that is true. They are skew. But if they look like this, then they are not. So our answer here is sometimes, okay? We have to think of every scenario possible. Number 3, 2 lines that do not intersect are skew. Okay, so we've got 2 lines that do not intersect. Are these 2 lines skew? Well, these 2 lines are in the same plane, so they're not skew, they're parallel. But these 2 lines don't intersect, but they're not in the same plane, so they are skew. So our answer for this one is going to be sometimes. All right, sometimes 2 lines that do not interact are skew like this, but sometimes 2 lines that do not intersect are parallel, and therefore they're on the same plane and not skew. Okay, number 4, 2 planes, each parallel to a third plane, are parallel to each other. This one's kind of hard to, I'm not going to be able to draw this, but think of it like this. You've got 2 planes, right? And they are both parallel to the plane in the middle. He's parallel here, he's parallel here. They're saying that now these 2 are parallel. Well, if this is equidistant from this plane and this is equidistant from this plane, then these two planes are equidistant from each other. This plus this, right? And that doesn't change anywhere along here. So that is always true. If two planes are parallel to a third plane, they are parallel to each other. That is always true. Because when we talk about equidistance, distances being equal, that never changes. All right? Let's look at number 5. Two lines parallel to a third line are parallel to each other. This is very similar right here. Consider these lines now instead of planes. Two lines are parallel to this third line, so therefore they are parallel to each other. And that is always true. Just like the planes being parallel to a third plane, the lines being parallel to a third line is always true because they are always the same distance from each other because they're the same distance from that third line. Number 6 reads, two lines parallel to the same plane are parallel to each other. Now, this one's a little bit different. Let me see if I have a small piece of paper. So here's our plane, and I'm just using a small piece of paper because I only have so many fingers. So we've got two lines parallel to this plane. Okay. And in this case, are these two lines parallel to each other? Yeah, possibly, right? But what about in this case? Here, we could say yes, because we could draw a plane. If I had another sheet of paper in another hand, we could lay it on top of both of these pencils, and it would be a plane that's kind of on an angle. It wouldn't be parallel to this plane, our beginning plane, but it would be a plane just the same. Okay, we could connect them with a flat piece of paper. That makes it a plane. So here, they could be parallel to each other. But if we turned our line, so our Sharpie line is parallel to our plane. Our pencil line is parallel to our plane. But are they parallel to each other? Could we make a plane that includes both of those pencils, both of these marks or writing utensils? No, right? This way we can't do it. So our answer for this one is sometimes. Sometimes two lines parallel to the same plane are parallel to each other, but sometimes they're not. All right? That's when we use the sometimes. We got to think of all the possible choices here. Let's look at number 7. If two planes are parallel, a line in one plane is parallel to the line in the second plane. Okay, so let me grab another little sheet of my cat paper here. I did that something else. Okay, so we've got a line in this plane and a line in this plane. Okay, and our planes are parallel. Okay, I'm going to put them like this. They're still parallel. They're just, I'm not covering one. Okay, and the question is, or the statement says, a line in one plane is parallel to the line in the second plane. Well, if I turn my lines and I line them up, okay, then I could create a third. Let me see if I can hold it that way. Oh, making me work today. I could create a third plane, right, that crosses both of those lines. So in this case, yes, they would be parallel. But if my line in my plane is going the other way, while my planes are still parallel, are my lines parallel this time? No, right? Their lines are headed in the different directions. So they can't possibly be parallel. They're skew. So for our answer here, it's sometimes. Sometimes our lines are parallel, sometimes they aren't. All right, let's look at number 8. Two lines skew to the same line are skew to each other. Okay, I've got to get another pencil out here. All right, so we've got two lines, okay, and they are skew to this line. And it's saying that two lines skewed to the same line are skew to each other. So we've got this line, skew to this line, skew to this line. Okay, these two lines, purple, the pencils are skew to the highlighter, right? They do not share a plane with that. So are they skew to each other? Well, the way I have them set up right now, no, right? Because there could be a plane in between here. There could be a sheet of paper that connects them. Because they could be in the same plane, they could be parallel. Now, if I turn this one slightly, my purple pencil is still skewed to my highlighter, and my red pencil is still skewed to my highlighter. And now if we compare our pencils together, they are skew to each other. So sometimes they're skew, right? But sometimes they're not. So our answer for number 8 is sometimes. All right. I know these seem ridiculous, but they're just trying to get you to think about the possibilities. You got to think in a spatial way, okay? Because these things are not, when we're talking about different planes, it's not that easy to visualize. I'm doing my best to help you, work through your problems in the same manner so that you can see exactly what they're trying to say. I'm a very visual person. I like to see things. Some people, some people can read these and just be like, oh yeah, sometimes, always, never. Okay. I'm not like that. I like to see things. All right. Number 9, a line that intersects one of 2 parallel lines intersects the other also. All right. So I've got a line and I have a parallel line to it. Okay. My purple pencil and my highlighter are parallel to each other. A line comes and intersects my highlighter. Okay, it crosses my highlighter, basically. Does it also intersect my purple pen, which is parallel to my highlighter? No, right? It doesn't intersect it. But what if my line went this way and intersected it? My highlighter. Okay, I can't draw it through my pencil, but I will go like this. It intersects my highlighter, right? And it also then would intersect my purple pencil. So this case, yes, it intersects both. But if my line went this way, then no, it only intersects my highlighter and not my purple pencil. So again, this leads us to an answer of sometimes. The final question is number 10. Through a point not in a plane are an infinite number of lines parallel to that plane. All right, so let me get my little paper out here. And we have to use a bit of imagination. Oh, you know what? I'm sitting at my sewing table, so maybe not. All right. So here is my plane. Let's envision that blue pinhead as a point not on my plane. And let's just forget about the actual metal pin part connecting them, okay? So here's my plane and a point not on my plane, right? My paper is the plane, the pinhead is my point, and we're ignoring the rest, all right? It says through this point in a plane, not in a plane, an infinite number of lines are parallel to that plane. So now we have to think about this point, and this is my line, okay? Here's a line, but if I turn it just slightly is another line. And if I keep turning it and turning it and turning it and turning it and turning and turn all the way, there are an infinite number of lines. Now I can't go this way, right? Because that's no longer parallel. That intersects it. But if I stay parallel, equidistant from this plane, there actually is an infinite number of lines that goes around and around this pinhead, okay? This one point. There are an infinite number of lines that go around, so that is always true. Now, there are even more lines that go down and intersect the plane, but because space is an infinite thing, there are an infinite number of lines that travel just on this point and stay equidistant from our plane, okay? So that's looking through the always, sometimes, never section. Okay, so then the bottom section of page 41, we have another definition, and it's called a transversal. And we are going to be using transversals extensively throughout geometry. We had one actually over here. This plane C was a transversal of plane A and B. They just hadn't taught you the word yet, so they didn't use it, okay? But here we're learning the definition. A transversal is a line coplanar with 2 or more other lines intersecting them in points other than at their intersection. Now that part is weird, right? Intersecting them at points other than their intersection. They're meaning, what they mean is T is intersecting M and N, not where M and N would intersect themselves. Okay, if we drew this out, eventually M and N would intersect somewhere off my page because they're not parallel, somewhere way over here, right? And T isn't crossing them there. That's what they're talking about with this other than their intersection. Some of these definitions are weird. That's what they mean. If eventually M and M touched each other, T is not crossing at that point. T is crossing somewhere else. Okay, so T is crossing these two lines. It is called a transversal. And there's a whole bunch of properties to transversals, and we're going to get into that. So looking at page 42, there's a ton of information, and it's super important information. All right, and it tells us when two coplanar lines, so remember that means they're on the same plane, okay, are cut by a transversal. So here's another line cutting across them, right? 8 angles are formed, and they've numbered the angles. 1, 2, 3, 4, 5, 6, 7, 8. 8 angles are formed, and these numbers are important. When we're talking about stuff here, you need to be able to remember what numbers are where, because it does matter. So 8 angles are formed, and here's how I like to think of it. I like to think of it as 2 boxes. Okay, 2 boxes are formed. Those are our angles. Angle 1, angle 2, angle 3, angle 4, 5, 6, 7, 8. Okay, now these boxes are related to each other in these different ways. Okay, so let's take a look at the different ways. Here are their special names, basically. Angle 1 and angle 2, angle 7 and angle 8. Okay, if you think about it, they're on the outside, right? They're on the farthest outside part of our drawing. So they're called exterior angles. Okay, they're on the outside of the two lines. Therefore, 3, 4, 5, and 6, which are on the inside or between our two lines, they're considered the interior angles. All right. Here's where it starts getting a little, that was easy. Here's where it starts getting a little bit more complicated, where I'm talking about these boxes, and it's good to know the numbers or the space in the box where they belong. 3 and 6, 4 and 5 are pairs of alternate interior angles. So 3 and 6 are considered alternate interior angles. They're both on the inside, but they're on alternate sides of this line, the transversal line. They're on different sides. And same with 4 and 5. They are in the interior, but they're on different sides or alternate sides of this transversal. Okay, so they're called alternate interior lines. Or sorry, angles. Alternate interior angles. So if we have alternate interior, then we have alternate exterior. So 1, and I'm going to put a triangle around it, I guess. 1 and 8, okay, they are alternate exterior. They're both on the outside, but they're on alternate sides of the transversal. Alternate exterior angles. Same with 2 and 7, okay? 2 and 7 are alternate exterior angles. Now, these different angles have relationships to each other, and we'll talk about them in a minute, okay? That's why we need to make sure we understand that they are related. 1 and 8 are related in a special way. 2 and 7 are related in a special way. 3 and 6 and 4 and 5 are each related in a special way, okay? Now, this last part talks about corresponding angles. And what I want you to think of when we're talking about corresponding angles, so I'm going to erase all the little marks I put in the middle, is here I want you to think about the box. Corresponding angles are angles that fall into the same part of the box as the other. So angle 1 corresponds with angle 5 because they are both in the same part of the box, right? They're both in the upper left-hand side of their box. Therefore, they are corresponding angles. They're in the same part of the box. 2 and 6 are corresponding angles because they are in the same part of the box. 4 and 8 are corresponding angles because they're in the same part of their box. 3 and 7 are corresponding angles because they are in the same part of that box. Okay, that's why I put that box around there, because then I can visually see what section of the box of each one is in. So now that we learned how all those angles are related to each other, let's see why it's important. Well, we know that when two lines are parallel and they're cut by a transversal, and this can be a cut at any level, okay? It could be at any direction, whether, you know, straight up and down, perpendicular, or on an angle like this. Parallel lines, when they're cut by a transversal, certain pairs of angles are the same. Okay, it says appear to be the same, but they are the same. So postulate 8 tells us if two parallel lines are cut by a transversal, then the corresponding angles have equal measure. Okay, remember when we were talking about corresponding angles, we were talking about the box, right? That being said, we know that the measure of angle 1 is equal to the measure of angle 3 because they are in the same part of the box. They are corresponding. Therefore, they are equal. The measure of angle 2 is equal to the measure of angle 4. They are corresponding angles. The measure of angle 5 is equal to the measure of angle 7 because they are corresponding angles. And the measure of 6 is equal to the measure of 8 because they are corresponding angles. Okay? That's postulate 8. And remember, please use your postulate and theorems page on all of your work, including your quizzes and tests. It's there for a reason, okay? Let's look at theorem 11 at the bottom of this page. It says if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other one also. Think about it for a second. If line T is perpendicular to line L, which means it crosses it at a 90-degree angle, right? And L and M are parallel to each other, which means they are equidistant from each other, never changing, then of course T would be perpendicular to this because T is running straight, L and M are running perfectly straight. Nothing's twisted or on an angle, because if M was twisted enough for it not to be perpendicular, then they wouldn't be parallel, right? They would eventually run into each other and they wouldn't be parallel. And on the next page, they give you a proof, although they've written it incorrectly, what they want to prove. So if you want to fix that in your book, you can. I'm not going to go through the proof. We're going to trust that we know if we have two parallel lines and a transversal is perpendicular to one of the lines, it is perpendicular to the other line. And how we know that is our box, right? We know that angle 1 is a 90-degree angle. Therefore, we know that angle 2 is a 90-degree angle because they are corresponding angles. They are in the same part of the box, so they are equal. If 2 is a 90-degree angle, that means T is perpendicular to M. Okay, that's what the proof is going to tell you, probably in a lot of other words. That is the basic function of what's happening here. All right, good job. Okay, on page 44, we've got another theorem. Okay, these first couple books, we're going to be pumping out a lot of theorems. That's why our theorem and postulate page is so vital. All right, theorem 312. If two parallel lines are cut by a transversal, then the alternate interior angles are equal. Okay, so we're given that line L and line M are parallel, and line T cuts across them. Okay, so they want us to show for this proof that angle 1 and angle 2 are equal. They're trying to prove that this is true. We're going to believe that it's true, but they're going to prove it. And here's how. If you have your boxes here, okay, angle 1 and angle 3 are equal, right? The measure of angle 1 is equal to the measure of angle 3 because, and I think it's right here, because if lines are parallel, then corresponding angles are equal, right? And these angles correspond. They're both in the same part of their box, right? Okay, then the next step is here. We can go straight up and say that measure of angle 2 is equal to the measure of angle 3, because what happens when two lines intersect? What kind of angles are created here? And this is our 2 and our 3. I took out the top line because I don't want it to be a distraction. These are, remember from before, these are called vertical angles. When two lines intersect, the angles opposite each other are vertical angles, and vertical angles are equal. Okay, so now we've proven that 2 is equal to 3, and we proved a step before that that 1 was equal to 3. So now we have two angles equal to the same angle. What does that tell us about those two angles? Right, that they're equal to each other through substitution. We can simply substitute this 1 for that 3 because 1 is equal to 3. They're the same thing. So the measure of angle 1 is equal to the measure of angle 2 via substitution. So we can trust Theorem 312. If two lines are parallel and cut by a transversal, then their alternate interior angles are equal. And that's the same if this was angle 5 and 6. Okay, 5 and 6 would be equal because they are as well alternate interior angles. Turning to page 45, okay, which is just past your test. You gotta pass the test, or well, I want you to pass the test, but you gotta flip past the test. We've got Theorem 313, and it tells us if two parallel lines are cut by a transversal, then the alternate exterior angles are equal. Okay, so we've been given two parallel lines. Our drawing shows that it's cut by a transversal. We don't have to include that in our proof. It's just there in the illustration. And they want us to prove that angle 1 is equal to angle 2. Okay, and this proof is very similar to the one we just talked about, but I'm going to work through it with you. Okay, so line 1, our part 1 for our statement is our given information. Line L, and I don't like that weird L that they do, so I just write it my own way. Line L is parallel to line M. Okay, that was given to us. That is given information right here. Okay, now remember, our to prove is going to be our final step. And we're trying to prove that 1 is equal to 2. First, to do that, we have to show that 1 is equal to something. And what can we show 1 equal to? Well, we can show that 1 is equal to 3, right? Because they are corresponding angles. If lines are parallel, then corresponding angles are equal. Okay, that was the theorem we just talked about. Now, remember when I told you before, I'm not going to be writing Theorem 311 or whatever it was, because the number of the theorem doesn't matter to me. And as you move forward and maybe have a different teacher at some point, the theorem numbers probably aren't going to match up because this theorem numbers are just based on this book. Okay, but as you move forward in math in college or something, they're not going to care if you remember that it's Theorem 311. They're going to want to know what that theorem means, what it is. So we just write it out. And you can use shorthand. If lines are parallel, then corresponding angles, that's what this is, and I've just put apostrophe S, are equal. And I just mark that by an equal sign. Okay, so now we've shown angle 1, and you can do this if you want, to be equal to angle 3. Visual people, that's what I like to do. Now I know angle 1 and angle 3 are equal to each other. What other two angles can I show are equal to each other? Well, if we look at 3 and 2, we can see that they are vertical angles. So we can say that angle 3 is equal to angle 2 because vertical angles are equal. So now we've also proven, and I'm going to use the same mark because they're equal to each other, that angle 3 and angle 2 are equal. Well, if angle 2 is equal to 3 and 1 is equal to 3, then we can say that the measure of angle 1 is equal to the measure of angle 2 through substitution. Okay, we put this 1 where this 3 is because they are equal and can be substituted or switched out equally. And therefore we can say the measure of 1 is equal to the measure of 2 via substitution. Okay, let's take a look at the rest of the problems on this page. All right, problems 312 through 318 start out with this drawing. And it tells us that given that line L and M are parallel and the measure of angle 1 is 60 degrees, find the measure of the other angles. So here's what I'm going to do. First, I'm going to draw my boxes because I like the boxes. And then I'm going to mark this. My measure of angle 1 is 60 degrees. Okay? Now, rather than solve it in the order in which they give me here, I'm going to solve it in a slightly different way. First, I'm going to think about all the different angles that measure, or that angle 1 is equal to. Well, if I think about corresponding angles, then I know that 1 and 3 are equal, right? Because they're in the same part of the box. So I know that 3 is 60 degrees. If I think that 1 is an exterior angle, then I know that 1 and 4 are equal, right? Because they are alternate exterior angles. They are both exterior, but on alternate sides of our transversal. So that I know that 4 is 60 degrees. Okay. What about, there's one more that it's still equal to. Okay. Angle 1 is a vertical angle to number 2. 1 and 2 are vertical angles. Vertical angles are equal, so that I know that number 2 is 60 degrees. All right, that's all of the different angles that angle 1 is equal to, right? It's equal to 2, it is equal to 3, and is equal to 4. Boom. Now, the next part I'm going to look at is I'm going to look at this being a line, and I'm going to draw it like this. Here's line L, right? And I'm just going to draw this top part of the transversal. Looks like this. Here's my 60 degrees. Okay? Here's angle 1 and here's angle 5. What does this remind us of? Well, this reminds us of opposite rays, right? Adjacent angles whose exterior sides form opposite rays are what? What's their relationship to each other? They're supplementary, right? Because this whole angle here is 180 degrees. So they are supplementary. If they're supplementary, I can take 180 and subtract the 60 that I have here and get 120 degrees. So I know that angle 5 is 120 degrees. Now that I have a different number to go with, let's think of all the things that angle 5 are equal to. Well, angle 5 is equal to angle 7 because they are corresponding angles, right? They're in the same part of their box. So angle 7 is 120 degrees. Angle 5 is equal to angle 8 because they are both alternate exterior angles. And in the future, I write this as alt exterior or alternate interior. You got to abbreviate, so much writing. Okay, 5 and 8 are alternate exterior angles because they're both in the exterior and they're on alternate sides of our transversal. So 8 is 120 degrees. All right, and there's one more relationship to 5, and that's 6. 5 and 6 are vertical angles, and vertical angles are equal. So we know that 6 is 120 degrees. Right? And then we've labeled everything. Okay, you don't have to go in the order that they're listed here. You go in the order you want to go in. All right, it's your math, it's your homework. You do it, you do you. All right. But using that process, we were able to figure out every single angle just by using all of the theorems and the postulates that we just talked about. Now I want to do another proof together, and actually we're going to do a couple of proofs here together. But I want to look at number 21 on page 46. Okay. Proof 21 on page 46 shows us that we are given line A and line B being parallel and the measure of angle 2 equaling the measure of angle 3. So we've got this angle just sitting out there. All right. And they want us to prove that 1 and 3 are equal. Okay. So first thing I'm going to do, before I even write down my given and on line 1, I'm going to mark this. I know that measure of angle 2 is equal to the measure of angle 3. It's given to me. So I can go ahead and mark it. As we go through this, I do a lot of markings on my illustrations. It's just how I process it. If you don't need to, then don't. But if you are, you're getting started here, we're just doing proofs, and I know they can be challenging. It might just give you that leg up if you start marking them so you can see what you have. All right, that being said, line 1 is that A and B are parallel, and the measure of angle 2 is equal to the measure of angle 3. That was our given information. Now, the next thing we need to think about is how are we going to get to here? We need to show that 1 and 3 are equal, not 2 and 3. So we have to think of, is there a relationship between either 1 and 2 or 1 and 3? Well, there's definitely not a relationship between 1 and 3, right? They're just out there. Unless the book told us there was a relationship, we're not going to be able to piece one together just yet. But if we draw our squares, our boxes, we can see that 1 and 2 have a relationship, don't they? What kind of angle are 1 and 2? What is their relationship? Yes, they are corresponding angles. The measure of angle 2 is equal to the measure of angle 1 because corresponding angles are equal. So we've proved that. Those are equal. Now we can mark 1 being equal. Now we have a relationship between 1 and 3, don't we? If 3 is equal to 2 and 1 is equal to 2, then we can say that the measure of angle 3 is equal to the measure of angle 1 because of substitution. Okay, we're substituting in the 2 for the 1, or sorry, the 3 for the 2, or however you want to think about it, substitution. Okay, 2 angles are equal to the third angle. They're equal to each other. That is a different whole theorem, but all we have to do is substitute, just like in math, right? If A is equal to B and C is equal to B, right? All we have to do is substitute this A for that B, and C is equal to A. All right, same process. That's 321. Let's look at 322. So for 22, we're given that C and D are parallel, and that the measure of angle 4 is equal to the measure of angle 5. Now this time they want us to show that 7 and 8 are equal. Okay, so we have to think, with 4 and 5 being set up, can we get to 7 and 8? Right now, 7 and 8 do not have a relationship. Proofs are all about relationships and how things work together. Okay, so we have to establish a relationship between 7 and 8. And all we've been given is that C and D are parallel and 4 and 5 are equal. They have a relationship. That's our given information. So our first step is to find a relationship between 7 or between 7 and something or 8 and something. Let me see what I did here. I started with the 7, okay? What relationship does 7 have? Okay. 7 is an interior angle, just like 4. They are alternate interior angles because they're on alternate sides of this transversal. So we can say that the measure of angle 4 is equal to the measure of angle 7 because if lines are parallel, then alternate interior angles are equal. All right? Alternate interior equal. Shortcuts, remember, we can't write it. They give you this much space. Got to abbreviate. I didn't even abbreviate here, but that's our shortcut. If parallel lines, then alternate interiors are equal. So now 4 and 7 have been shown to be equal. Now we could say 7 was equal to 5, but that doesn't get us where we need to go. We need one extra step this time because we're talking about 8. So now we need to have 8 to have a relationship with something. What's the only thing right now we can show that 8 has a relationship with? That's right, it's 5, right? Because they are vertical angles. 2 lines are crossing, intersecting, and these vertical angles are created, these angles opposite each other. So we can say that the measure of angle 5 is equal to the measure of angle 8 because vertical angles are equal. So now we have 8 equal to 5, right? So now we have 4 equal to 7, 7 equal to 4, 4 equal to 5, 5 equal to 8. Now we need to do our substitution, right? Angle 4 equals angle 5. Angle 4 equals angle 7. Angle 5 equals angle 8. Okay, these 4s and 5s can be interchanged, and then we end up with the measure of angle 7 being equal to the measure of angle 8, which we can visually see because we marked them, right? And we did that through substitution. Substitution is going to be a huge reason that we use constantly. Substitution, substitution, substitution. What can we substitute for something else? Well, we can always substitute equal things. It's just like when you cook. Okay, there's substitutions you can make, but they have to be equal. If they're not equal, then you're not really substituting, you're just making a different recipe. Okay, here we substituted because they are equal parts. Okay, and that's proof 322. If we turn to page 48, we'll see over the next couple pages, we've got 2 postulates and 2 theorems. We're going to just go through those and see what they have to say. Postulate 9 reads, through a point not given on a line, or not on a given line, one and only one line can be drawn parallel to the given line. So if we have a line and a point, there is only one line that can be drawn that is parallel, equidistant at every single point from our original line through the point that we were given. Okay, that was one of our homework problems for a little bit further back, right? We had a point not on a line. Well, here's the postulate that supports that that is true. Postulate 10 tells us if 2 lines are cut by a transversal so that corresponding angles are equal, then the lines are parallel. So now we're not dealing with a given knowledge that lines are parallel, but they're telling us if we have 2 lines that are cut by a transversal and corresponding angles are equal, we can prove these 2 angles or any other corresponding angles equal, then we've proven that the lines are parallel. So now they're not giving us parallel lines, but we're proving that the lines are parallel. Okay, a lot of postulates and theorems are going to work that way. One will say one thing, the other one will be the contrapositive, right? Or the reverse. Okay, theorems. Theorem 314. In a plane, if 2 lines are perpendicular to a third line, then they are parallel to each other. Now remember, last one we talked about was we had 2 lines, and if we had a line perpendicular to one, then it was perpendicular to the other because they were parallel. Now, we don't know if they're parallel yet, but we've got this transversal coming through, and each one of these lines is perpendicular to the transversal, therefore they're parallel to themselves. They're perpendicular here, that means they run in the exact same, they run the exact same way, okay, next to each other or any distant apart from each other, honestly, but they run exactly the same as each other. They will never cross, otherwise this wouldn't be a 90-degree angle. And they give you the proof for that here that you can read. Theorem 315 says if 2 lines are cut by a transversal so that alternate interior angles are equal, then the lines are parallel. So again, remember before we said if the lines are parallel, then alternate interior angles are equal. Now we're doing the opposite. If the alternate interior angles are equal, then the lines are parallel. Okay, again, here's a proof that can show why that theorem is true, but we're just going to go with it, okay? So like I said, remember, your theorems and postulates page is crucial. Please keep it with you. Then, turning to page 50, we have our last new theorem of this section of this video. And it reads, if 2 lines are cut by a transversal so that the alternate exterior angles are equal, so we are given the fact that these are equal, then the lines are parallel, okay? We can say that the lines are parallel because of this theorem, right? Again, it's the switch from the last one that we did, where if we had parallel lines cut by a transversal, we had alternate exteriors equal. Now we're starting with the alternate exteriors equal and proving that the lines are parallel. So let's take a look at, we're going to look at this proof, okay? So our first statement, we're given the fact that angle 1 is equal to angle 2, and I've marked that on my drawing. They want us to prove that the lines are parallel, okay? So our first statement and reason is our given information. Angle 1 and angle 2 are equal, and that was given information. Now we need to develop some other relationship in this drawing, and they're kind of helpful at first when we start doing these because they're labeling basically the other relationship that we want to use. Okay, if we look at our boxes with what they've given us numbered, we have corresponding angles here, right, between 2 and 3. But that doesn't help us yet because first thing we want to do is discover and list the relationship between 1 and 3. 1 and 3, we are at a point where two lines intersect and they are opposite angles from each other. Therefore, they are vertical angles. So we can say that the measure of angle 1 equals the measure of angle 3 because vertical angles are equal. All right. Now we've got that. We can't just say that 2 and 3 are equal because they correspond because we don't know that these lines are parallel yet. And remember, those corresponding angle things only worked if we knew the lines were parallel. But now we're trying to prove them to be parallel. And at this point, we do have corresponding angles that are equal, right? We have to state that they're equal. So we'll do that next. The measure of angle 3 is equal to the measure of angle 2. And I wrote corresponding angles are equal, but honestly, that is not correct because that is only true if our lines are parallel, and we haven't proven them to be parallel yet. But I can say substitution because I'm substituting right here, right? 1 is equal to 2, 1 is equal to 3, therefore 2 and 3 are equal. Substitution or transitive property. Either one of those works, okay? Now that I've proved that 2 and 3 are equal, I can say that line L is equal to line M because if corresponding angles are equal, then lines are parallel. That was the postulate that we just learned, right? If corresponding angles are equal, then the lines are parallel. Now, as we did this together, you could see that I made a small error right there, right? Do not freak out if you are doing proofs and your proofs aren't exactly the same as the answer key when you're checking your homework. Because when I grade proofs, I read through every single step that you list, and I see if the way that you did it, it will work or not. You do not have to solve this proof exactly like the book says. But I do check every single line to make sure that your proof will work. Now I want to continue on page 50 and let's look at the next couple of problems. It asks us to write the converse of these statements, and then is the original statement true or false? Is the converse true or false? Write true or false for each statement and its converse, right? So the original statement is if each of two angles has a measure of 28 degrees, then the two angles have equal measures. Well, is that true or false? Okay, that is a true statement, right? If they both equal 28 degrees, then they are equal measures. Now let's write the converse of that. If the two angles have equal measure, then each angle has a measure of 28 degrees. Now, is that true? If the two angles are equal, can we just say that they're 28 degrees? No, they could be equal to any number of degrees, right? So our converse is false. I want to look at one more of these, number 28. If two angles are both obtuse, the two angles are equal. Is that true or false? Well, not all obtuse angles are exactly the same, so that's a false statement. All right, now let's write the converse of that. If the two angles are equal, then they are both obtuse. All right, that's our converse. And is that correct? Well, two angles can be equal but not be obtuse, so that is also a false statement. All right, looking at page 51, number 332 and 333. It asks us to name the segments, if any, that can be deduced to be parallel in the figure shown. Okay, so we've got lines, we've got this shape here, right? Looks like a parallelogram, but can't be 100% certain. It's definitely a quadrilateral. We've got some numbers and some letters, right? So it asks us, when the measure of angle 3 which is here, and I'm just going to mark it lightly so that I can see what's going on, equals the measure of angle B. All right, what can we say, if anything, is parallel? Well, here's how you have to think about these kinds of problems. I'm going to pull out my little straight edge, and I'm going to draw an extension of that line. And I'm going to draw an extension of this line, like a transverse, right? So if this AB is transversely cutting AD and BC, and I have what looks like corresponding angles to be equal, what lines can I say are parallel? If these corresponding angles are equal, then line AD is parallel to line BC. Okay, just because they cut it short doesn't mean you can't extend it so you can see better what exactly they're asking about. Let's look at 33. When the measure of angle 1, now let me erase my markings here. I'll keep my boxes for now, but when the measure of angle 1 here equals the measure of angle B. So now what is the relationship between angle 1 and angle B? Well, if we look at our boxes here, they're both on the interior, right, between our two lines, and they're both opposite or alternate sides of our transverse. So therefore, 1 and B are alternate interior angles. Because alternate interior angles are equal, that would tell us that our lines are parallel. So again, we could say that AD is parallel to BC. Okay, so that's what you're going to do and continue working. There's only a couple more problems with that drawing. I want to look at the next illustration though, because it's a slightly more complicated one, and I want to talk us through it. All right. All right, if we look at problems 336 and 337, they are in reference to this drawing. Okay, now this drawing has a lot going on, a lot of information in it. There's just a lot going on. So I want to take this one part by one part. So let's look at 36. When the measure of angle 2, and I'm going to mark it, is equal to the measure of angle 6. So again, where'd my straight edge go? Timeout. I found it. Okay. What we can easily do is extend our drawing. Okay. We're not breaking any rules. We're just doing it so that we can visualize what's happening here. So we've got two lines. They're being cut by this transversal, which is DB, right? And when it cuts it, we've got angle 2 equal to angle 6. Well, those are interior angles, and they are on opposite or alternate sides of our transversal. So that tells us that DC, okay, and we can even just mark it as a segment because in this drawing, technically it's just a segment. DC is parallel to AB. Okay, that's what we can tell when those two things are true. Okay, I'm going to just mark it lightly, so I'm going to erase it so that I can do my next problem. When the measure of angle 1, which is here, equals the measure of angle 6, which is here. And when we're looking at this one, if we consider the same transversal that we had before, it doesn't really give us much, right? So here's what I did. And you just have to turn your book, but since I got papers everywhere, it's a little bit harder for me. I redrew the drawing, right, on a different sheet of paper. And again, we're talking about angle 1 and angle 6, right? Here's what I want you to do, though. If you turn your book sideways and we extend our drawing still, okay, we want to keep looking. Now, does that change it? If we're looking maybe at AD and BC as being our edges, and this is our transverse, does that change anything for us? Well, no, right? Because our alternate would be 5. And so it turns out that this has none. These two have no relationship, therefore we can show no lines parallel to each other. But what I want you to consider when you do the rest of these is if you turned your shape and considered the other sides to be the top and the bottom, would your transversal then give you information like the fact that 8 and 4 are alternate interior angles? Okay, so if you need to turn your book so that you can see what's exactly going on, please feel free to do that, because it will be helpful in moving forward when you're trying to figure out what's what, and especially answering these questions, because I know there's a whole bunch more. All right, before I end this video, I want to look at 2 more proofs. We're going to be doing a lot of proofs in the future. You're actually doing a lot of proofs in this work, so I want to make sure we're working through some together so that you can see the process. So looking at number 45 on page 52, we've got this drawing. And we're given the fact that angle 2 equals 122 degrees, and I'm just going to mark my drawing. And angle 3 equals 50, oh my word. That was aggressive. Click there. Angle 3 equals 58 degrees. Okay? That's what we're given. And they want us to prove that line L and line M are parallel. Well, we've looked at a couple of different theorems now that could help us get there. So we need to think about the relationships that 1 and 3 have, not just with each other, but with the angles that are around them. That being said, we know that our number 1 is going to be our given information. The measure of angle 2 equals 122 degrees. The measure of angle 3 equals 58 degrees. That is our given. Now I'm going to start with this area here with my angle 3 and relationships it has with other things. All right. So the first thing I'm going to do is show the relationship between angle 3 and angle 5. And I do that like this. Okay. I say that angle 3 and angle 5 are supplementary angles. And how can I say that? Because their exterior sides, which is out here, form opposite rays, right? Opposite rays are all collinear. It's forming this line, and their 2 angles are inside. So basically they're doing this, right? They're forming opposite rays, and they're inside of it together. We know that this half circle basically is 180 degrees or supplementary. Okay, so I can say that 3 and 5 are supplementary because their exterior sides form opposite rays, which is this theorem. All right. Now that I know that they're supplementary, I can give 5 a value. Now I can't just jump to it. There have to be some steps when we're changing over from a word statement to an equation. We have to be careful. But once we're in an equation system, then we can add and subtract things. So let's take a look at that. Our next step then would be to say that the measure of angle 3 plus the measure of angle 5 is 180 degrees. And we can say that because that's the definition of supplementary angles. Okay, right? Supplementary angles equal 180 degrees when you add them together. That is the definition of supplementary angles. And this definition of will be a reason quite a bit. We'll use that a lot. It's the definition of this. It's the definition of this. It's what we're basically saying. That's what supplementary angles mean. All right. So now we've shown that together they equal 180. So now I can actually add and subtract. See, I'm in an equation now. I can add and subtract so that I can say that 58 degrees, which is measurement of angle 3, right? That's the same thing. Plus the measure of angle 5 equals 180. And I can say that by substitution, right? I just substituted the actual measurement of angle 3 for the words measurement of angle 3. Now I can take the next step. How did I get from here to here? I subtracted 58 from both sides. So I use the subtraction property. Remember when we learned all these properties? This is what for. This is why. So now it shows that the measure of angle 5 is 122 degrees. Right? I've proven it. And those are the steps we took to get there. So now what is my next step? Now I actually see a relationship between angle 2 and angle 5, right? They're the same. So that's where I'm going to go. And I can say that the measure of angle 2 equals the measure of angle 5. And I can say that by substitution because 122 degrees and 122 degrees is the same thing. Okay, 5 equals 122 degrees, so I can substitute angle 5 right here where it says 2 equals 122 degrees. So I substituted. All right, now I have angle 5 equal to angle 2. If I look at their boxes, what are angle 5 and angle 2? What is the relationship between them? Right, they are corresponding angles. They're in the same part of the box. So they are corresponding angles, and that's how we're going to end our proof. We can say that line L is parallel to line M because if our corresponding angles are equal, which we've proven that they are, then the lines are parallel. Okay, and that was the postulate 8 we learned on page 43. You can list this here like that. I really just do it because while I don't normally make videos for these types of lessons, I'm standing up at a board, I can note that while I'm talking to my students. That's why the note is here. I actually worked through all of this stuff just like you are working through all of this stuff right now. Okay, I didn't just cheat it over from the teacher's guide. So we've proven that our corresponding angles are equal. Therefore, our lines are parallel. Okay, we solved our proof, and that's proof 345. All right, the last proof I want us to do together is 349, and that is on page 54. All right, it's this weird shape. I don't know who writes these books, but okay. All right, and we are given the fact that the measure of angle 1, which is here, plus the measure of angle 5 equal 180 degrees. We're also given the fact that the measure of angle 1 plus the measure of angle 4 equals 180 degrees. And they want us to prove that YZ, which is this ray going this direction, is parallel to UV, which is the ray going in this direction. Okay, if we were, I'm not going to look for my straight edge right now, just to extend that and extend this, that's more typical then of what we think about when we think about transversal lines, and then we can draw our boxes in, right? Okay, step 1 is, of course, our given information, right? They give you 2 lines, and I wrote on both lines, but I only have to write one given because they're all just given. Okay, so I wrote my given information. Angle 1 plus 5 is 180. Angle 1 plus angle 4 is 180. That's our given information. Okay. Now, we need to establish a relationship between 5 and 4. We can do that right here from our given information by rewriting it like this. The measure of angle 1 plus the measure of angle 5 equals the measure of angle 1 plus the measure of angle 4. They're equal, right? They both equal 180 degrees, so they're equal to each other, and we can do that by substitution. Okay, we just substituted that for this. All right, so we can rewrite it like that because of substitution. All right, now we have a measure of angle 1 on both sides, and we want to get rid of it because we want our measure of angle 5 and our measure of angle 4 to be the only relationship here. All right, so we do that like such. The measure of angle 5 equals the measure of angle 4. How did we go from step 2 to step 3? We subtracted that measure of angle 1, right? If we subtract a measure of angle 1 from both sides, then we get to this point where now our 5 and our 4 have a relationship with each other. And that was the subtraction property of equality, okay? And you can, just like before, you can write property of equality if you want, POE. All right, now we see that 5 and 4 are equal. If we think of our transversal as line UT right here, what relationship do they have? They're not corresponding angles, right? But what are they? They're both interior angles, and they're on alternate sides of this transversal. They are alternate interior angles. And what do we know about alternate interior angles? We know that our line YZ, it has to be parallel to UV because our alternate interior angles are equal. Therefore, our lines must be parallel. okay? I don't expect you to have all these theorems and ideas memorized just yet, or even after a week of doing this stuff. So please, please use your postulates and theorems page to help you work through this, all right? There's a lot of theorems. This is what geometry is. We're just going to be piling more and more on as we go. And our point is to get from step 1 to step 4, or sometimes 8, 9, in a good fashion, okay? And like I said, yours does not have to look exactly like the book. If you can find a different way, because in proofs, there are different ways. When you get more tools in your belt, there will be different ways to solve this problem. And so as long as the way that you did it makes sense, okay, and it's in the proper logical order, then I'm fine with that. I grade each proof individually. Those are all I'm going to go over with you today. You're doing a great job. I know it can seem like a lot. Use your postulates and theorems page. Until next time.